All right, guys. So 1 and 2 of this review. So number 1 should be pretty easy. This one is going to be all of them influence the rate. Okay, because we know that concentration, right? If you have more reactants, that'll increase the rate. So you increase the concentration, you're going to increase the rate. Nature of reactions is another way of saying the state of matter. Is a solid, liquid, gas, or is it like powder or pellets? So we know that if we increase the surface area, we will also increase the rate. Temperature, we know, also affects the reaction rate. You increase the temperature, you're going to increase the rate. And then we know that if there is a catalyst, that will also increase the rate. So even if you didn't know what one of them meant, like maybe you didn't know what nature of reactants meant, you can see from the other ones that they do influence the rate. And so you would pick E as all the above. Okay. All right, let's go to 2. 2 is, it could have been a little tricky if you were expecting to just see the energy diagram for a reaction. But if you take a look at this, this is not a reaction rate energy diagram, because the one that we've been looking at, it is energy, and this is the x-axis is reaction progress. But if you take a look at this graph, what's on the y-axis? It's number of molecules, right? So what it's graphing is it's graphing the amount of molecules that get through, that go through the reaction. And if you notice, what is the thing that changes in this graph? Yeah, activation energy changes. What is the only thing that we know of that affects activation energy? Catalyst. So it's going to be catalyst. Okay, just remember, all these other things affect the rate, but catalyst is the only thing that affects the activation energy. Yeah. It does affect the activation energy. That's how it increases the rate of the reaction. So think about enzymes in your cells, right? It does speed up the reactions by lowering the activation energy. Yeah. All right. Any questions on 1 and 2? Okay. So pretty simple. This might have been a little tricky if you didn't see the number of molecules on the y-axis. But let's take a look at number 3. So number 3, we are going to skip this. And the reason why is because it's not on the AP test anymore. If you take a look, the question is asking, it's asking for the rate of appearance of B at a certain amount of time. When it asks for the rate at a specific amount of time, it is called the instantaneous rate. And you guys don't need to write this down. And the way that you calculate instantaneous rate from a graph is you need to use calculus to calculate the slope of the tangent line at that specific point. Yes, bringing you trauma if you have if you're taking pre-calc or calc. It is not on the AP test anymore. There's no calculus on the AP chemistry test, just algebra, so we don't have that no more. So you guys are blessed, because when I took AP Chem, we had to do it back in my day. All right? So you will not get anything like that. All right, let me see. You guys can do 4, 5, 6, and 7 on your exam or on your own. So let me give you guys about 5 minutes to try that, and then we'll go over it. So if we take a look at the ratios of O2 and O3, we can see that is 3 moles of O2 for every 2 moles of O3, right? And so what we just need to do is just compare the ratios. So if the rate of disappearance of O2 is 0.6, right, so 0.6 molarity per second, we just need to compare that ratio with the disappearance of O3. So this is going to be molarity per second. And so you can just do the algebra to calculate for it, but your answer is going to be 0.4, okay, 2/3. Okay, because you have 2/3 the amount of O3 as you do of O2. Okay. Okay, for number 5, pretty easy. overall rate order is you just add the exponents. So A is second order, B is first order. So that means you have a total of third order. Okay. Okay, for number 6, you might have had to do, if you didn't memorize it, you'll have to calculate, but it's pretty simple. We know that the rate is equal to the rate constant times your concentration, so molarity, and whatever order it is. Now, it tells you that it's a second order rate constant, so second order. So that means it's going to be molarity squared. Okay, what's the unit of measurement for rate? What's the unit of measurement for rate? Yeah, molarity per second, right? So molarity per second. All right, so we're just working with the units of measurement here because it's just asking for the units. So molarity squared is the same thing as molarity times molarity. So just so that we can see it a little better, I'm going to expand it out. And you, in order to isolate K, you need to divide by this. So dividing by molarity like that will cancel them out. And then on the bottom, you will get molarity times second, but it's on the bottom of a fraction, so the units of measurement will be per molarity per second. We know that molarity is the same thing as moles per liter, and so we just need to look for the ones that make sense. So if we take a look right here, we don't see molarity on here, so we're going to have to expand it out to moles per liter, right? So let's just expand this out. Let me make a little bit more space. Molarity is molarity over, or sorry, moles over liters, right? So this right here can expand out to 1 over moles over liter. And then we got times second on the bottom. Now, if you have a fraction on a denominator, what you do is you just move the denominator of the fraction in the denominator to the top. So the liters right here would go to the top of the fraction right here. Okay, so liters is on top, moles is on bottom, so this will be liters times moles negative 1. Seconds is always also on the bottom, so seconds negative 1, so that'll be C for units of measurement. So this is kind of testing your algebra to see if you know what to do if you have a fraction on the bottom of a fraction. So C is going to be your answer. All right, let us go to the next one now, number 7. And for number 7, it tells us the information that we need to know to write the rate law, and then we just need to plug our information in. So we have this reaction right here. So we know that the rate is equal to the rate constant times the concentration of the reactants, and we need to plug in the exponents with their reaction order. It tells us that it's first order for both of them, so we can just keep this the way it is. We are looking for rate. It gives us K and it gives us the concentration. So K will be 6.1 times 10 to the negative 2 liters per moles per second. So I guess molarity negative 1, my bad. Molarity negative 1, seconds negative 1. And then the concentration for I is 0.1 molarity. The concentration for OCl minus is 0.2 molarity. And so you just need to multiply all three of them together. Okay, any questions with the setup? Okay. All right, so you do your math, just get B. Can units of measurement work out as well because this cancels out with this. You get molarity per second. Alright guys, I'll give you another minute to finish up and then we'll start going over it.
He's my cat. Switch. Switch.
Okay guys, let's go over the next couple. Okay, so if we take a look at 8, it tells us the reaction and it gives us the rate, and we can see that it is second order. Okay, so that's a key thing right here, because it tells you that when the concentration is 2, the rate is 0.106, and it's asking what is the rate when it's when it's 4. So we're comparing how the rate changes when you change concentration. So if you take a look at the molarity, how did the molarity change? How did the concentration change? Did nobody do this? It doubled. Okay, this doubled. So the concentration doubled, and we're looking at how the rate changes. If this is second order, what happens to the rate when you double the concentration? It's going to quadruple. So all you got to do is quadruple what the rate was, and then you should get D. Okay. So here, we're looking at how the rate changes with concentration. Double the concentration, we see that it is second order because the exponent's 2, and so we quadruple the rate. All right, let's go to number 9. Number 9, it gives us the rate law right here. Okay, and the equation, and it's asking what happens to the rate when just NO is doubled. Now, this is pretty simple because we just need to look at NO. Now, if you look at NO, what order is NO? It is second order. So if we double NO, what's going to happen to the rate? Quadruples. Yeah, so C. Okay, so super simple. It's pretty much the same concept as number 8, just kind of packaged a little bit differently. Okay, number 10, very similar. This time we just get a table. So if you look, 8, 9, and 10 are like the same type of problem. It's just the way that it's formatted. For this one, it gives us this reaction right here and wants us to get the rate law. So we know that the rate is equal to K, concentration of the reactants, but we just need to figure out what the exponents are. So let's start with A. To get A, we need to keep B constant. So we're going to keep B constant. So we're comparing 1 and 3. What are we doing to the concentration when we look at 1 and 3? It doubles. And when you double A, what happens to the rate? Yeah, there's no change. So what type of order reaction is this? 0 order. So A is 0 order, which means it's going to disappear. And we don't even need to do work anymore because you can see the only one that has 0 order for A is A. So it's going to be A. Okay, and if you actually wanted to do the comparison, you'll see that B is second order, because if you kept A constant and you double B, you'll see that the rate quadruples, which is second order. So B is second order, A is 0 order. All right, so number 11 is connected to number 10. So it's asking what's the ratio of A's rate of disappearance to C's rate. So we're comparing A's rate to C's rate. And for this, we need to look at the mole ratio. If you look at the equation, the coefficient for A is 2. so it'll be 2. C's rate is 1, so it'll be 2 to 1. Again, the order matters. It's asking about A compared to C, so A is going to come first in the ratio. It's very easy to put D if you're not keeping track of what comes first, but just keep that in mind. And I think I said this like 5 times already, but a question like this will be on your test, so just make sure that you're careful with the wording. Whatever you're comparing, the first one comes first in the ratio, or the numerator on the fraction. All right, any questions on those 4? All right. Okay, so for this one, it tells us that it is first order. Okay, so if it is first order, that means we have to look at the AP equation sheet and use the first order concentration equation, right? So if you have your AP equation sheet, this right here is the first order one. So remember, they go in order 0, 1, 2. So we are using this equation right here, the second one in the kinetic section. Okay, so we're going to use that equation, and we just plug in our values for each variable. AT is our final concentration, which is what you're looking for, because it's asking the concentration after 450 minutes. You plug in your initial concentration, which is 0.11. It gives you the K value right here, 1.33 times 10 to the negative 4 per minute. And then the time is 450 minutes. So you just do your algebra, just make sure you're careful with the negative signs and whatnot. And then to get rid of the natural log, you have to put everything to the power of E. So it'll be E to the power of negative 2.266, and that'll give you 0.104 molarity. And that's going to be B. But if you look at 13, it's asking for the rate constant for a first order reaction, and it gives us the actual half-life. So before we solve it, let's just talk about some of the things that you should know. What's the unit of measurement for rate constant? Or what's the variable, sorry? K. Okay, and you're looking at a first order reaction, and you're looking at half-life. Now, there is an equation that involves K for half-life, and it's actually on the AP equation sheet. So if you take a look at your AP equation sheet, and if you did not label this already on your equation sheet, make sure you guys do. But this equation right here is the half-life equation, but it's exclusively for first order reactions. Okay, this only works for first order reactions. So on the AP test, I mean, it's possible that you might get half-life for 0 or second order. If you do that, you can use these equations. Just make sure that your final, your AT, is half of your initial. But typically, you're going to get half-life for only first order reactions, and this is the equation for that. Okay. So this is what we're going to use for this problem right here. Half-life is 0.693 divided by the rate constant. So that's all we have to do right here. So half-life is going to equal 0.693 over the K. And you are solving for K. So let me give you guys about a minute or two, see if you guys can solve this and finish up number 13. After that, see if you guys can do 14, 15, and 16 on your own. So you'll be finishing 13, and I want you guys to do 14, 15, and 16 on your own as well. Okay. So let me give you about 4 minutes. These are pretty easy questions, so make sure you guys do that, and then we will move on. It's how they collide versus how they rebound, how they bounce off each other. Okay, so for number 13, you just need to plug in your value. So if you rearrange it, you are solving for K, right? Because you're looking for the rate constant. So it'll become K is equal to 0.693 divided by the half-life, which is 85 seconds. And it's going to give you 0.00814. There's a missing decimal here, but it should have been A. Hopefully you guys were able to take that educated guess on that. So my bad. I didn't make this document, but that's an error there. Okay, 14. It's asking what fraction of a reactant remains after 3 half-lives in a first-order reaction. Now, you can do the math if you wanted to and plug it into the equation and whatnot, but let's just think about it logically. After 1 half-life, how much is left? 1/2, right? And then you got another half for the second. And then another half, which is 1/8. So after 3 half-lives, there is an 1/8 left over, and it'll continue to go down like that. All right, we're going to do 15 last because that's a steady step. So if you didn't notice that, that's what it is. But let's do 16. We're looking at factors that do not influence the rate of a reaction. So let's just go through them and figure out which one does not. So does collision frequency affect the rate? Yeah, because the whole point of chemical reactions is you want the molecules to bump into each other. So frequency matters, so that can't be correct. Does the amount of energy they bring into the collision matter? Yes, that's activation energy. Does the orientation matter? Yes, the positioning matters as well. That's also activation energy. So the last one is rebound, and you guys can probably deduce we never talked about rebound, so how they bounce off each other, and so that is going to be our answer. All right, any questions on 13, 14, and 16? You guys good? Because we're about to do steady step. All right, let's do our steady step for number 15, and then we'll move on to the last portion of the review. All right, so if we take a look at 15, we got the reaction mechanism, and if you look, the second step is a slow step, right? And so the rate should technically be K is the concentration of C, but what's the issue with this rate law?
On the end and the reaction.
Yeah, it's an intermediate, right? It's consumed in the reaction. So we cannot use C in our rate law. So we have to use steady step. And if you remember, the rate forward is equal to the rate reverse. And then we just plug in our values. So rate forward is the forward constant times A and B. And then for the reverse, it'll be K reverse, and it's just going to be C. And we just want to rearrange this for C, so we divide by the K reverse. So divided by KR. And then we plug in our values for C. Now, all of the rate constants can be summarized as K overall, and then it'll be concentration of A, B. So our answer will be C. And just a reminder, for the steady step, you do need to show your work for this. You can't just put this right here, KAB.
What?
That's just the way the point totals work. And it'll be helpful when you take the test. I am. All right. Let's go to the next set. I want you to try 17 through 20 on your own. And these are all related to this chart right here. So you're going to need this chart. If it's hard to see, pull it up on your screen. But 17 through 20, I'll give you about 3 minutes to do this. This shouldn't be too bad. And then we will finish off the review. All right, so number 17, we got a reaction coordinate, and we're just figuring out some information about it. So 17 is asking what letter corresponds to activation energy? Which letter is activation energy? B, yes, it is just the height of this hill relative to the reactant. So B is the activation energy. Okay, which one has to do with the enthalpy change?
B. Which is
Ooh. So it could either be A or C technically, but the only option you have is A, so A. But A or C. Okay, yeah, they're both the same. If you take a look at this, they're both the same thing. Okay, either works. It's just the difference between the reactants and the products. All right, we're looking at the reverse reaction. Is it exo or endo? Reverse. Reverse is endo because the products will be higher than the reactants. Forward is exo. And then what does the catalyst change? It is. What does okay? So conceptually, what do catalysts change? Activation energy. Which one of these is activation energy? Is it any other? No, it's just B. Okay, just remember, catalysts only change activation energy.